right, good morning. I'll try and keep this quick and exciting, and I'm going to be covering this at a fairly high level. I'm going to save a lot of the technical details, questions and answers, because there's a huge scope that I'm about to present. And if I were to delve into all the minutia of all the different technology areas, we're going to need lunch and dinner. So let's not go that far unless you have a very specific question. Next slide, please. What are we going to be talking about today? We're going to be talking about what NASA does as a whole and provided how does that fit into sustainability here on Earth. Okay. We work in space, which is an incredibly demanding area. And for anybody who does any sort of engineering work, you try and get rid of any of the complications. Well, going into space does the exact opposite. We add all sorts of complications just because it's kind of exciting. Along that way, we're going to talk about how we implement or plan to implement an ecosystem in space. We have spent 10,000+ years here on Earth developing a commercial infrastructure. It is culminated in the online purchasing processes that we have today. If you want something, by and large, you can go online and buy it. Well, how do you do that on the moon when you're 300,000 kilometers away from your nearest FedEx drop box? Okay, it's a little difficult. So here are some proposed ideas that we absolutely are looking to put on. And then we're going to tie this all back to how what we're doing in space takes effect here on Earth. Next slide, please. All right, this is just the general NASA slide. Yes, we're nationwide, but if you happen to notice, we've got two very important centers here in Cleveland, Ohio. We've got a fundamental research center, which evaluates technologies from your beer stain napkin that you come up with in your most creative hours, all the way through to flight hardware. So we cover the entire gambit. We also have a test facility, a fairly large test facility outside of Sandusky, Ohio, that is capable of testing very large hydrogen systems. And right now we're in the process of implementing and building up a couple of new fuel cell facilities up in Sandusky, Ohio, to support a regenerative fuel cell for lunar surface applications. Next slide. This is, again, a template slide. Dr. Kurt Sackstedler, he knows more about this than I do by a long shot, but NASA does not work in a vacuum, no pun intended. We work with the environment, the community at large. We work with universities and small businesses and large businesses because we're in this together. We happen to be working as a team. And yes, we may be the quarterback, but we need a running back. We need wide receivers. We need an offensive line. And I think you might know a little bit about needing an offensive line every once in a while. So if you have questions, please contact us. Next, please. All righty, this is a quick overview of what NASA is trying to do. We're starting off here on Earth. We have to understand the environment that we live in so that we can take that environment with us and survive in the vacuum of space or in the very harsh surface of the Mars environment, okay? So we're going to learn about what we're doing here on Earth and how it is that human beings can survive. And then we're going to try that on the crucible of the lunar surface. I mean, at the lunar night, you run into an environment where it's 100 Kelvin. The oxygen that we breathe would turn into a liquid, okay? And that's just at the lunar night. When you go to the lunar day, depending on where you are, you're anywhere from 105 to 125 degrees Celsius. I know I'm mixing my units here for the engineers, but bear with me. So you're going from liquefying oxygen at the cold to boiling water at the hot. Human beings don't survive well in either environment. So we have to get our equipment and human beings to survive in both. And part of the reason why we're doing this on the lunar surface is because it is such a constrained environment that we have to learn sustainability from our first pencil sketches. We are tracking each milliwatt. We're not tracking the nearest terawatt, certain applications here on Earth. We're tracking milliwatts and milligrams. And you have to put that level of detail into your technical assessments. you're pushing the boundaries. You're creating wonderfully new technologies that can be used in far less constrained environments. So this is why we're looking at trying to understand where we are now and how we carry that with us through the rest of our exploration of the solar system. Next slide, please. All right, as part of that, and this is focusing on just the hydrogen economy. Number one, how do you get the hydrogen? Okay, it may sound like a simple question, but when you go on the lunar surface, there's negligible hydrogen. There is more gold in the Yukon than there is hydrogen on the lunar surface. So we need to get the water on the lunar surface and electrolyze it. Okay. Now the fundamental electrochemical process for turning lunar water ice into hydrogen and oxygen is the same as here on Earth. It's just so much more polluted on the lunar surface. So if we can take that contaminated water on the lunar surface and bring that technology here on Earth, third world countries would benefit immensely from the reduced complexity of the water purification system to generate the hydrogen to support the hydrogen economy. Okay, here in the more industrialized worlds, it reduces the costs of the hydrogen production facilities that we would need. And that's just the water electrolysis. Now that you have the hydrogen, what do you do with it? Well, I think most of us here would recognize fuel cells are the answer of choice. But we have to ask which fuel cell. For certain applications, solid oxide technologies make sense. Okay, how do you make a solid oxide system durable enough to survive launch, rigid enough to survive the hot and the cold temperatures, and thermally cycle times? Anybody who's dealt with the ceramic technology knows that's a bit of a challenge. PEM technologies, they're great. They do exactly what we want to do. We've demonstrated them here in cars for decades. How do you get them to survive in the really cold environments? Yes, we're going to insulate them. Yes, we're going to heat them, but it's still much colder than we would face here on Earth. Plus, they have to work with pure oxygen. Here on Earth, that's generally considered an accelerated stress test of the membrane, the catalyst, and the catalyst support. But here in space, it has to be on pure oxygen for all 50,000 hours of operational life. That's a demanding task. And if we could figure out how to do that for the lunar surface, your cars, your hydrogen fuel cell powered cars are going to last significantly longer. What is not on this slide is the cryogenic hydrogen and cryogenic oxygen management. NASA has been doing work in those areas for decades, and we're trying to transfer that knowledge to interested parties so that they can take advantage of what we've already learned. Next slide, please. All right, I have to put this slide up there because, well, this is what NASA is doing. Everything for the space exploration of the lunar surface is under the Artemis umbrella. So if you have questions on that, this is the first stop. Next slide, please. The Artemis program is divided into 6 areas. I'm not going to be covering these in detail, so you don't have to bring out your pillows right away. You can wait for later in the presentation. Next slide, please. These particular areas are where hydrogen and hydrogen sustainability fits into the conversation. Now, for the space launch systems, the hydrogen and the oxygen come from here on Earth. Okay, right now, the space launch system is the largest single consumer of hydrogen on planet Earth by no small margin, at least 2 orders of magnitude. Unfortunately, for the hydrogen economy, that will need to become one of the smallest consumers of hydrogen as we move forwards and transition away from a carbon-based economy. I'll talk about the surface systems and the CLIPS layers here in a moment. Next, please. All right, Artemis Base Camp. Presuming that we get to the lunar surface safely and we're ready to do what we need to do, how do human beings survive in that environment? How do we have the electrical power to do all that we need to do to keep the air breathable, to stay warm, to stay cool? How do we communicate back with Earth? And more importantly, how do we move around on the lunar surface where you are moving in a substance that is more abrasive than any sandpaper that you're going to find? Okay, it is an extreme challenge. It is an extreme mobility challenge. But before you can move, you have to have the power. So that's where the fuel cell technology comes in. We still have to keep the astronauts alive. We're using electrolysis to take the processed water that the astronauts generate through metabolic means to recycle and breathe the oxygen that is produced from the water electrolysis. And I'm running a little behind, so I'll move on to the next, please. All right, exploration. As we're moving around, we need to explore the permanently shadowed regions where there is the highest concentration of lunar water ice. But that's when things start to get really cold. So you need a lot of power to stay warm. You need a lot of mobility so that your wheels stay operational at those subcryogenic temperatures. Okay, that's a challenge. And if we can bring those technical solutions back to Earth, then that will help us significantly improve our fuel cell powered cars. Who knows what else it's going to improve along the way? Next. Okay. Now, this is kind of the engineering eye chart. For those of you who are engineers in here, these are the only numbers that we're going to be thinking about. And the reason why it's important enough to consider in here is for space application, mass is king. The heavier something is, the more expensive it becomes and the more restrictive it is for your space exploration. Okay? So if you can save, for example, 1 kilogram on Earth, that's 20 kilograms on the launch pad. Now, if you're launching a little small satellite, who cares? Okay? In the grand scheme of things, that's not a big deal. But when you're delivering a multiple metric ton system that's as small as we could make it to support human operation, all of a sudden, when you're talking about a couple of extra kilograms, that gets expensive. That gets mass intensive, and that means we have to have multiple launches. Multiple launches means a lot of money, means a lot of hydrogen. So one way to get around that, next slide, please, is to develop a commercial network or develop some sort of infrastructure. And this eye chart, I have no expectation of anybody taking away anything other than, yes, it's complicated. What this is a simplified chart of taking water ice and the lunar regolith and processing it. Sometimes using techniques we have here on Earth, sometimes developing all new ones, but developing those technologies so that we can get the raw materials and the hydrogen and the oxygen that we need to sustain operation on the lunar surface. And along the way, next slide, please, we're learning a lot about ourselves. Because one of the definitions of sustainability is to live within the resources available to you. And if you're tracking each milligram and each milliwatt, that forces a whole new level of concern for sustainability. And if we can develop that sustainability for the lunar surface, it will help us here on Earth. Any questions?